Hello, welcome back. So, now we will start another new topic, which is probably the most important separation process for minerals. This is called in general flotation, because earlier it used to be called froth flotation, but there are now many other say actually the various designs and the various techniques are also adapted. That is why I prefer to use it as a general term called flotation. If we look at the history of this, in 1869, William Haynes patented a process of separation of minerals and gangue using oil. Now, you see that so far whatever we have discussed about the separation processes, they are based on the principle of primarily based on the size and density, and fundamentally they are based on the movement of solids in fluids with some additional your forces or maybe some kind of your design features, that how will you collect the product, how will you say increase this settling phenomena and all sorts of things. This is entirely a different phenomena, that it is primarily based on the surface chemistry based phenomena, that is when two particles they have your differences in their surface chemical properties, that is your surface properties based on the so that is called the your flotation process. So, here you see that what it is saying, that William Haynes patented a process of separation of minerals and gangue using oil. That means, you added some chemicals, that oil in general we call it chemical. So, which he called bulk flotation. So, the flotation name was first given by Professor William Haynes. In 1896 to 97, another two scientists, Frank Elmore and Stanley Elmore, set up the Glastead copper mine at Lentelid, Dolgello in North Wales, where they carried out the world's first commercial flotation process in 1897. So, this was the basic invention and this is the your commercial operation. However, in 1900, C.V. Pater and G.D. Delpratt independently in Australia invented the modern froth flotation process. So, these two are generally called the inventor of the modern froth flotation process, in which initially fatty acids and oil were the flotation reagents to enhance hydrophobicity of the valuable minerals. Before we get into the next slide, let me explain you, otherwise you may be distracted, that what happens when you have a very fine particle size ranges. Why should you have very fine particle size ranges? Now, as the grade of the minerals, that a grade of the ores is deteriorated over time, it demands that your liberation size becomes finer and finer. Now, most of the minerals these days, they are liberated below say 100 micrometer sizes. Most of the cases they are below even 60 micrometer sizes or maybe below 40 micrometer sizes. So, at those sizes, it is very difficult to have a separation based on their size or density. So, in that case this new technique was adopted, that is, if we put water and if we try to mix them into a water, some surfaces of the minerals or the ores, the water gets easily attached to. Some surfaces it is very difficult that water gets adhered to. So, when the surfaces they are having a liking towards the water, that means the water gets easily adhered to the surfaces of the ore particle, we call them as hydrophilic particle. And when the water gets repelled from the surfaces to get adhered to, we call them hydrophobic. But many times these differences in the relative hydrophobicity is not that obvious. So, what do? We try to add some fatty acids, or say in simple terms, let me some oily material, so that this oily material sit on your targeted material particle surfaces, and which will make the particle surface hydrophobic. That is the, and then what you do, that is once you have a separation between the two particles based on the hydrophobicity and the hydrophilicity, then by some intelligent means, if you have that to take them out in the separated stage, then you can have a separation possible even at that finer size ranges. And how we do it, what are the chemicals we add, when do we add, what are the effects of different chemicals, what are the machines we use, what is the chemistry part of that, what are the design part of the different machines. These are all the subject matter of this your lecture series on this topic called flotation. So, flotation is undoubtedly the most important and versatile mineral separation technique, and both its use and application are continually being expanded to treat greater tonnages and to cover new areas. Set aside the mineral part, even if you look at that your some other applications, that is in place of minerals in some other areas also, I will explain you where are those. Even the flotation technique is being used for separation between the two phases. Flotation has permitted the mining of low grade and complex ore bodies, which would have otherwise been regarded as uneconomic. If you remember that your consideration for your economic efficiency, which tells that your ultimately what is the contained value per ton of your material and what are the cost of the processes of extraction, that is that includes starting from mining, mineral processing, metallurgical operations and all this. Now, what is happening when, as I said, that normally we have seen that as we go down the seam, that is when mining as a bed of your particle layers, that is your ore bodies, how they are formed, they are having a bed. So, when you are going down the earth crust, that is if you are going deeper and deeper, whatever you are mining, they are having lesser and lesser quantities of your wanted materials, and it is almost true for almost all the minerals. Now, that demands when it is low grade, that means assay content is very less. So, in most of the cases it demands that it has to be ground to very fine particle sizes. Now, the gravity concentration technique fails to do that, we have explained that it has got a upper size limit. Below a certain size limit, the efficiency drops significantly. So, the entire process becomes economically not viable. So, if this process was not invented, maybe the mining engineers would not have thought of mining such a low grade and complex ore bodies. Many times as the grade may be good, but the way it is distributed across the matrix of a mineral, that again it demands that very fine grinding. So, this is what I try to say, that flotation has even permitted the mining of low grade and complex ore bodies, which would have otherwise been regarded as uneconomic, that is, would not have even mined them. In earlier practice, the tailings of many gravity plants, that means what we are throwing out as a tailing of a gravity concentration process, that your gravity concentration process cannot process it further because of their fineness, were a much higher grade than the ore treated in many modern flotation plants. So, it was initially developed to treat the sulfide minerals of copper, lead and zinc. This was primarily developed targeting the processing of mainly copper and then also lead and zinc. Now, the flotation has expanded to include even nickel, platinum and gold hosting sulfide minerals, and to non-sulfide minerals including oxides such as hematite, cassiterite and non-metallic minerals such as fluorite, talc, phosphates, potash and energy minerals like fine coal and bitumen. We can add many more. Flotation process now also finds application. This is what I was just mentioning, that outside the mining industry, like de-inking of recycled paper pulp, that is, when you try to recycle your papers, that is used papers, you will have some inks into that. How do I take out that ink? This is where again the flotation process is being used. And de-oiling oil refinery effluents, and this is mentioned by this gentleman Rawlins in 2009 article, and these are for examples. So, what I try to emphasize upon here, that what is the importance of this process for to the modern mineral processing engineers or the scientists who are busy in this field, or maybe dreaming of a future, dreaming of having a future in this area, that without having much knowledge in flotation or the flotation process in general, you will probably not called as a good mineral processing engineer. And this is why I want to spend say more time on discussing this aspect, that is your flotation process, in subsequent lectures. Although it is a very vast subject these days, so I would try to just brief you about certain aspects of this process, which I think that in this introductory course it should be told. So, as I said, that flotation is a physico-chemical separation process that utilizes the difference in the surface properties of the valuable and gangue minerals. Earlier we have seen that we are trying to separate the valuable and gangue minerals based on their size, means is the hardness or maybe some other properties, that is your, we say it is based on size or density. Here we are trying to utilize the differences in that physico in their say surface properties, it is a surface chemical properties we say. So, how do we do it, and what are those surface properties we try to exploit, that I will explain to you. Froth flotation involves three different phases, that is solid, that is your fine your ore powder or maybe fine ore particles, liquid, that is your water, and a froth phase. Froth phase means it is a, you have got solid particles, you have got water, but in that froth phase you have got air bubbles and you have got some kind of your oils and all this. So, it is just like your foam type of material, that is when you are cleaning your clothes with some kind of detergent, what you get, that is your some solid particles like in the form of dirts and then your air bubbles and then water also. So, that is called the froth. The process of separation of mineral includes three important mechanisms. One is called true flotation. I will explain it later on. That is your selective attachment to air bubbles. That is what happens once I have made them one particle group as your hydrophobic, another particle group is hydrophilic. Then what we do? The particles which are hydrophobic, they are generally aerophilic. So, we try to generate in situ some air bubbles and this hydrophobic particle gets adhered to this air bubbles, that is surface of this air bubbles, and because of your natural buoyancy, the air bubbles try to rise up to a vessel and then they have on the top layer, that is the froth phase, and then we try to take out those froths and the air bubble when they burst because of the atmospheric pressure and many other reasons, and then we take out that, we recover those particles separately. I will show you in subsequent pictures and the diagrams that how it is being done. So, one is called, so when the selective attachment to air bubbles, that is called the true your flotation, that means the bubbles or the particles which are hydrophobic, they will selectively get adhered to the bubble surfaces. Selectivity means the particles which are hydrophilic, they should not get adhered to the particle bubble surfaces. So, that means only your hydrophobic particles are being lifted up by the air bubbles. There is a process called entrainment in the water which passes through the froth. That means, when the water is also, I said that in the froth phase you have got water also. So, when the water is going up because of certain disturbances you have created in the water bodies in a vessel. So, this water will have certain amount of rising velocity. So, some particles may also get entrained in the froth phase along with the water. This is a little bit complicated thing. I will try to explain you a bit on this later on. Then there is another process called aggregation, that is the physical entrapment between the particles in froth. That is, the particles were already there and the froth phase has been developed and they are just entrapped there. They are just entrapped into that your froth phase. So, with this diagram I would like to explain you a bit, that is what is this process and how it is being done. See, this is the, suppose we call it a froth flotation cell, and here you have got a feed in the form of again the particle mixture, that is your wanted and your unwanted, and your water. So, you have fed it here and that is your slurry now. So, that is your feed in the slurry form, it is there, and you have got some, with this feed material you also add some chemicals here, that is, say suppose it is some oily material, oily type of material you have there. So, now you have got an impeller here and that impeller rotates. So, when the impeller is rotating, so it is creating a motion to the entire your slurry, and that slurry, and because of that the particles will not settle because of their masses. So, you are trying to create a turbulent atmosphere here, so that the particles are not allowed to settle because of their size and density, that is because of their masses. And the another purpose is that studying that the particles are homogeneously mixed or dispersed into the slurry stream inside the container, inside this vessel, that is your flotation cell. Now, what do we do? This impeller many times this part is made hollow, and the impellers also they have got perforations, and you inject air at certain pressure. So, you are rotating it and you are passing air at certain pressure. So, when you are sending pressure air at certain pressure, and this air will try to go out through this your perforations what you have into the impeller blades. Now, when this air compressed air passes out through these impeller blades, automatically there will be some bubble formations of various sizes, air bubble formation of various sizes. You have fed the slurry along with, or you may have added some chemicals here to make some particles intentionally those surfaces hydrophobic, and some particles are inherently they are hydrophilic. So, what will happen? These bubbles, because of the your pressure difference, because of the buoyancy, they will try to go up, retaining their your say bubble shape and the bubble structure. So, when this particle bubbles try to go up, these hydrophobic particles if they get adhered to the surfaces of the bubbles, and the bubbles start getting concentrated on the top layer of this. That is how a simple, if you are washing your clothes in a washing machine. So, that is say your rotation, that is basically you can say that that is the your like your impeller, and that is where basically you are rotating, and then because of the rotation you are creating some kind of your vortex flow, and there you have got entrained air, and that entrained air is basically generating your air bubbles. So, here you are just trying to push some air at certain pressure inside that, so that the air bubbles are formed, and you see that on top of your washing machine that there will be some foam formation, and similarly on top of this your fluid layer you will find that there is a froth layer, we call it froth layer, it is like almost like a foam. So, what is this froth layer consists of now? Now, this froth layer is having the air bubbles, you have got the water, you have got the particles which are hydrophobic particles, and you will have some kind of your oily materials also what you have added. So, this froth layer mainly consists of air bubbles, water, and the hydrophobic particles. Now, you should have some kind of your mechanical arrangement that to remove this froth, because the froth if they are too viscous, it is very difficult to have a your to let the froth move, but you can if you know that how to control the viscosity of the froth layer, and then if you have some mechanical means, suppose a scraper, and you are just scraping it out and then collecting this froth separately into a launder. So, that means you have collected now your hydrophobic material here, and while transferring your some of your air bubbles will automatically burst, and because of the consistent air pressure, atmospheric pressure you have, and because of many other reasons, and you will be now collecting your much lesser quantity of water than what you have fed, because the water at the top layer will be very less, because you are having a thick froth layer, and then you have got the particles, and now you can. So, basically you have concentrated your hydrophobic particle now into this launder. So, you have got a, and you have left your hydrophilic particle inside the your flotation chamber. Now, you should have some means of taking out your hydrophilic particles from the container to make it the continuous process. So, this is how you can have some kind of opening here through which you can take out by some means the your hydrophilic particles. This diagram I would like to show you, say suppose how the particles get adhered to the bubble surface and how they are transported. Suppose this is the lighter color is representing the hydrophobic minerals and the darker colors they are representing the hydrophilic minerals. So, initially when the air bubble is formed, maybe the selectivity is not there, maybe the both hydrophobic and hydrophilic particle they may get adhered to the surfaces of the bubbles, because it depends on what is the volume percentages of the bubbles you have generated. So, and then what are their sizes, what is, so that means what is the surface area of this bubble you have got in relation to the particle surface area you have inside your froth flotation cell. So, when the bubbles are getting adhered, particles are getting adhered to the surfaces of this bubble. Now, the bubble has to rise from here to here. So, there is some time left. Within that time, if the hydrophilic particles or hydrophilic minerals, they will get dislodged from the bubble surfaces. And ultimately, when the bubble has reached to this stage, that is your froth stage, majority of these hydrophilic minerals, they will get dislodged and they will come back to the flotation cell, and that is how you are selectively carrying upward your hydrophobic minerals. So, this is in short how it works, but when I have described it, you have understood that how difficult it is to control everything. What are the things we have to take care of? That is, first thing I will start with, that is say suppose the impeller, at what RPM it should be rotated, what should be the design of my blades, and then at what is that air pressure I should have, what should be the your dimensions of my say perforations, that is about this your impeller and your air and all this. Then how do we control the bubble sizes and their size distributions, how whether we need more stability or less stable bubbles, because if they are too stable, what will happen, even they are not dislodged. So, I will be having a much thicker froth layer which will be difficult to take it out. So, and then how do I make the particles hydrophobic and hydrophilic selectively? How do I ensure that only hydrophobic particles are say reported in the froth phase? So, all these things create the problem or the challenges to the mineral processing engineers, that how do I perfect it, and this is what I am going to talk in detail, that what are the various aspects. So, there is a machine design aspect, there is a chemistry related aspect, there is a bubble phase related aspect, then the material characteristics, the reagents what we should use, and then how we will be collecting the products, that is your from the froth phase as well as from your flotation chamber. These are all the finer details of this process, which we will talk in subsequent lectures. Till then, thank you very much.